Okay, welcome back, guys. We are on to 5.3. This is now integrals within polar coordinates. Just going to say in polar. Really quick review. Recall when we did integration in rectangular coordinates, you've got this function, and you go into the domain and you break it up into little pieces. And for every one of those pieces, you generate a rectangular prism. And the whole key to integration in two variables is that we know what the volumes of these prisms are. And there's two parts. There's the area of the base, which we call delta A. And this has a length in the x direction, a length in the y direction. So it's a product of two lengths. And then there's a height, and it's the function evaluated at some special spot, x, y. So then the volume or the change in volume is this height f times this base area delta A. So that's the whole insight right there. For rectangular coordinates or Euclidean coordinates, XY coordinates, blah 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 blah. Now we want to extend those ideas because lots of times the symmetry or the geometry or whatever you're working with is such that it makes more sense to think about things in polar coordinates. So this is just two dimensions, which is real quick. Uh, when you talk about polar coordinates, you specify an angle. I'm going to call that theta 1. You could specify a different angle. Maybe this angle here is theta 2. And then between theta 1 and theta 2, there's this whole spread of choices of theta. And then let's go with a different color. For any one theta, so let's say theta 1, you could specify an R1. You could specify an R2. I could go to this different theta, and I could use the same R1 and the same R2. So there's one more color to keep it all clean. So like that point right there is, we usually put R first. R2, theta 2. This one is R1, theta 2. This is R1, theta 1. And then this one is R2, theta 2. Okay, that's how those things work. And then you can kind of see, you can generate regions according to these coordinates. And if you have constants, so theta is between theta 1 and theta 2, and R is between R1 and R2. So sorry, I actually shouldn't have gone that high up. Let's go like this. Let's just make this real clear. Just go this far here. Boom, 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 boom. Right, so we're going between R1 and R2. We're going between theta 1 and theta 2. That right there is called a polar rectangle. Right, it's constant bounds, but not in Euclidean coordinates, in polar coordinates. So now let's say you are getting creative and you decide you want to replicate the ideas of integration that we've already seen in X and Y and Z, but you want to use a polar rectangle and you want to think about your coordinates as being polar coordinates. So let's say like this region here is what you want to integrate over. And you've got some function, and maybe the function looks like that. And something is going to happen. And let's try to make it very clear, and then we're gonna confront it. Let's look at this little region and compare it to that little region. What you want to observe as best you can is that this delta R, the amount that the radius is changing here, could be the same as that one right there. And the way we've got this drawn here, the change in theta is the same as well, right? Why is it that the area of this little gold region is so much smaller than the area of this gold region if they've got the same delta R and the same delta theta? If you're thinking along with this video, take a second and just ask yourself if you know why that's true. It is of fundamental importance in mathematics to understand the difference between measuring an angle, let's say, and measuring a length. So if that right there is delta theta, the angle has gone from whatever this angle is to whatever this angle is. This down here is that same delta theta, and we can even go way farther out. And then again, up there, it's the same delta theta. Angles are not lengths. On the other hand, and this is something I'm just going to say because you're supposed to know it before this class starts. This is like a geometry fact, maybe high school geometry. If this length is R1 here, that length right there, that arc length right there is R1 delta theta. If theta is measured in radians, this is the whole reason why people care about radians, why we use the radian measure. If on the other hand, you consider this length here, we'll call that R2, then this length here, that's a 2, is R2 delta theta. R2 is bigger, therefore the arc length is bigger. And therefore, we have to specify there's an R value here that's multiplying by delta theta. And down here, it's a different R value, right? Whatever R is down here versus whatever R is there. So I guess you could say R1 and R2. So let's be clear. The area of any one of these little rectangles, they're not really rectangles, they're little polar rectangles. They look like this. If you wanted to know what the area of one of those is, you would have to know the R value. And I'm going to say roughly because, hold on 1 second. I'll be a little more clear in a second. Roughly R delta R, or we'll put delta theta first. Delta R. This right here is this length. And then that guy right there is this. Now we say approximately because if you have a rectangle like this, and this is the height and this is the width. Of course, the area is the height times the width. We don't really have that shape, do we? We've got a slightly oblong shape. And so it's not really the case that the area is equal to I'll say the height times the width, where this guy up here is the width and this guy's the height, but it's close. And it gets better and better as we get smaller and smaller. So we are allowed to use it as an approximation. Okay, let's take a look at this again. So there's one ingredient that's still missing. At any one of these little shapes, you've got to generate a volumetric piece. And you do this by incorporating the height And the height comes from knowing what the function that you're working with is. So that's the height right there. And I want to multiply the height by my change in area, which is, well, there's an amount that the radius changes, delta r. And then there's also, I'll group it all in one, r delta theta. So this is now a volume. I've got three length coordinates. This is the height. This is one direction in the base. This is the other direction in the base. And that in total is how much volume is in that one little chunk of a prism that we made. So when we go to add all this up, you want to say, well, I would like to put meaning. So let's call that blue region in there R. I want to do a double integral over R, capital R. Right, that blue region is R. I would like to integrate a function in polar coordinates with respect to the area. As always in calculus, with integration, we have to appeal first to something like maybe a Riemann sum. And in this case, you're going to use a Riemann sum. We have to get a whole bunch of these rectangular prisms. And let's go with, we'll do the same thing we did when we did X and Y. These don't both have to be N, but I'm going to make them both, yeah. So J will correspond to all the choices in theta that we're making, theta 1, theta 2, theta 3, theta 4. And I will correspond to all the choices in R we're making, R1, R2, R3, R4. So for any one I and any one J, we can go to Ri, theta J. Maybe I'll draw this out over here just to be very, very clear. So you've got theta 1, theta, or sorry, R1, R2, R3, R4, R5, R6, R7, etc. Theta 1, theta 2, theta 3, theta 4, theta 5, theta 6. And it generates all these points. You get the idea. And for every single one of these points, we sample the value. And then we need to keep track of how much R is changing. And how much the arc length in the theta direction is changing. Sorry, I skipped one thing, my bad. I'm trying to build this from scratch. This is not the answer. The real integral is this limit if it exists, which for our purposes it will. 1 second. For that, please. J equals 1. All right, that limit if it exists. And the point is, if you look at what we just wrote there, this is equal to this. And sorry, this should be Ri here. We're sampling R. And now look. This is an integral with a new integrand. I want to write it this way, dr d theta. instead of thinking about it like we're integrating in polar coordinates with respect to the area, we can put this function r and the function f together as one integrand. And now we get dr d theta, which is the same thing, let's say, as dx dy or du dv or anything else. We already have a means of doing integration iteratively, right? First we do dr, then we do d theta or whatever. The fact that we're doing polar coordinates is encoded by that r right there, encodes polar coordinates. So one more time. If you start off trying to find this volume in polar coordinates, you start off with your height being this function f. But this extra r term comes in to account for this volume deformation, for this way that the polar coordinates work differently with volume near the origin than they do with volume farther from the origin. So that function r appears, but you reorder things so that you group that function r with f. Now it's a different integrand, but we don't care. We can evaluate this integral no problem because we already have techniques from the last section that we did for directly evaluating an iterated integral, a dr and then a d theta, or a dx and then a dy, or a du then a dv. We don't care what letters you're using, it doesn't really matter. And so the upshot, let's put it over here. The upshot of that whole analysis is the following. Oh, where's the rest of the divided? I'll put it like this. Given, we'll just do a polar rectangle for now. Or no, 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 no. Let me say one more thing. So I do want to conclude what all of this means here, but I want to define one more thing first. So we don't want only talk about polar rectangles. We're going to say if you have a polar region, so here's your there's two choices of theta, and you've got some function r of theta, we'll call it r1 of theta. So it doesn't have to be constant. It could be like this. That's r1 of theta. And then you've got some other r2 of theta. I don't really need this one down here. Function of theta. Then the region between the two of them, which is not a polar rectangle, is a polar region. So real quick definition. If you have a set and you can write it this way, all points are theta such that theta we can use a and b instead of I think people like a and b or maybe alpha and beta. So let me get rid of that theta 1 and theta 2 there. And instead, let's call it alpha and beta. This is common. Alpha is less than or equal to theta is less than or equal to beta. So those are my bounds on theta. And then r has to be between these two functions. r1 of theta is less than or equal to r is less than or equal to r2 of theta is a polar region. Okay, now I can say the upshot of the previous analysis. If you want to do a double integral over a polar region of a function in polar coordinates, you can write this in the following way. You can have theta go between two bounds, the two bounds, we'll call it d theta. That's the outside integral. Inside of that one, you can have r go between the two bounds, r1 of theta and r2 of theta. And now this is the way we've set this up right now. Mathematically, you can't tell this is polar coordinates. This could be Euclidean coordinates. I've just told you there's two bounds on the outside variable. There's two bounds on the inside variable. And you've got this function f that you want to integrate. If you want the number that comes out to be the volume in polar coordinates, you must also multiply by r. And I'll say this one more time. This triplet here, r dr d theta, is the little polar volume element, polar volume element. I'm not really defining this, so I'll put quotes on it. You need that factor of r there for the triplet to actually encode volume in polar coordinates. Okay, so this whole section is just about doing integrals over polar regions and making sure you understand that r factor always has to appear. And then also just so you get used to these things, like you've got to convert functions in x and y to functions in r and theta, and just a lot of calculation practice. So let's just start banging out examples one at a time, and we'll get as far as we get. Yeah, so I'm gonna take my time so you guys can have a few good examples here. They want us to sketch this one, so we'll just sketch this. R is so you can use D, R, whatever, they use R. 1 less than or equal to R less than or equal to 3. 0 less than or equal to theta less than or equal to pi. Okay, this is super easy, but okay, theta equals 0 is here. Theta equals pi is over here. So we're in this region. R, the radius R has to start at 1, and then here's 2, and then here's 3. So if we use R equals 1, theta between 0 and pi is all those points there. And then theta equals 3, R between 0 and pi is all those points there. It's like a half of an annulus. Here's the region here. Okay. Nice, easy, quick example. Let's do another one. Yeah, here we go. They ask us to evaluate this 3x dA over the region R. And this time R is similar. 1 to 2 and 0 to pi. Okay. So first things first, this is a good example. Obviously, we're going to integrate it in polar coordinates. This is what this whole section is about. The function is not expressed in polar coordinates. So we need to change that. And this is, I guess, calculus 3 knowledge. I forget where this comes up, but you have to be able to convert from Euclidean to polar. And in this case, it's just 3r cosine theta. Right? That r cosine theta, that is x. R sine theta is y. Okay, so with that in place now, I look at my region and I say, well, there's bounds on R, there's bounds on theta. Let's put the bounds on theta on the outside, the bounds on R on the inside. And I've got this function I want to integrate, 3r cosine theta. And I've set this up, dr d theta. I'll just say it again. Mathematically, this expression cannot tell that you're in polar coordinates. You've just got bounds and numbers and letters. This could easily be something in Euclidean coordinates. If you want this integral to represent volumetric, units like we just did in polar coordinates, you must always multiply by an extra factor of r. That's really what we're learning up until this step right here. From here, we're just executing r cubed cos theta from 1 to 2 d theta. So that right there is the integral in r. Because it was 3r squared, that integrates to r cubed. This gives me 8 minus 1 is 7. And if you integrate the cosine, you get the negative sign, which comes out to be 0. So those two steps, that's just a blast from the past, stuff we've done before. Getting from some problem formulated geometrically, or maybe stuff with x and y, and knowing how to convert it properly to a polar integral with that little factor of r multiplied on in, that's what we're learning right now. And then, as always, you've got to be able to calculate. So there's the calculations there. Okay, pretty easy, I suppose. Okay, this is another one. Yeah, let's do this one. They ask us to do this. And they just tell us R is the unit disk. So in particular, to circle center of the origin of radius 1. Okay, first things first. Let's say you weren't in calculus class, so you didn't know that you were expected to do polar coordinates. Why use polar coordinates? It's not that you have to, but you see the region that you've been given is this disk. It lends itself to polar coordinates. It looks like it would work well with polar coordinates. So maybe you say, I'm going to try it. I need to have the function that I'm going to integrate expressed in polar coordinates. Maybe you're used to the fact that x squared plus y squared, that is r squared. So you can just write this as 1 minus r squared. But you could also say, well, it's 1 minus r cosine theta squared minus r sine theta squared. And then you guys know cosine squared plus sine squared is 1. So that just comes out to be 1 minus r squared. So one way or another, you have to get to this conclusion. Now you've got a function to integrate. You need to choose bounds correctly. They didn't give us bounds. You've got to choose them. So here we go. I need bounds on, let's do theta first. I want a full rotation of the circle. So I'll go 0 to 2 pi. And then I want to start at the origin and go out to this radius of 1. So I'll take r from 0 to 1. I'm integrating the function 1 minus r squared. And now we're used to it. I know I'm going to do it. I'll multiply an extra factor of r on in there, dr d theta. That's what we're learning right now. From here on out, it's just stuff you've got to be able to calculate. That looks like pi over 2. Right, so there's r minus r cubed integrates to r squared over 2 minus r to the fourth over 4. You plug in 0, you get nothing. So you plug in 1, you get 1 minus 1/4, or 1/2 minus 1/4 is 1/4. Pick up an extra factor of 2 pi. Yeah, nice and simple. Onward. The heck is this one? No, we don't need that. Yeah. Okay, so now let's get into polar regions that are not just rectangles. What's next? What the heck are they saying here? One second. I gotta see. I gotta look at what they mean by this. Oh, is that right? They say the polar axis. I've never heard anybody use this term before. Region bounded by the polar axis and the upper half of the cardioid. Yeah, that's there's no reason to put that way. Okay. Anyways, let's just do it. So they want us to integrate this function, r squared sine of theta. They tell us, I mean, they put it in for us, r dr d theta. So they want us to evaluate this, and it's over the region D. And so this is how they describe the region. D is bounded by the polar axis. So they just mean where theta equals 0. But I guess that's not bad terminology. I just don't know anybody who ever says that. D is bounded by the polar axis and the upper half of r equals 1 plus cosine theta, the cardioid. Okay, so cardioids, this is something you guys would have learned to draw in Calculus 3 for sure. They look kind of like this, hence why they call them cardioids. It looks kind of like a heart. But we want the upper half and the polar axis theta equals 0. So our region is this guy here. So we're going to take theta from 0 all the way over here to theta equals pi. Now, this is getting a little tricky to visualize, but let's be clear about this. For any one choice of theta, we will start at 0 at the origin, and we will go as far as 1 plus cosine theta. If you were in a different direction, you would still start at 0, but now you're going to go as far as, not quite as far. This is a new 1 plus cosine theta. And then you can see it starts to get even smaller over here. 1 plus cos theta, etc. Okay, so let's just try to set this integral up correctly. We're going to take theta from 0 to pi. We're going to take r from 0 to 1 plus the cosine of theta. And they already told us what they want us to integrate. R cubed. Whoops. Sine theta, dr, d theta. Now this is going to be a little bit, no, this one's not so bad. I think this one's not so bad. Let's see what happens. Okay, 0 to pi. If I integrate r cubed, I get r to the 4th over 4. Times the sine of theta, d theta. And if I plug in 0, of course, I get nothing. So this all here is that inner integral. Take a moment. What am I supposed to do now? This is what is a u sub, right? The derivative of the cosine is the negative sign, so I can pull out a negative sign. And now this is u to the fourth over 4 du. So this integrates to u to the fifth over 20, 0 to pi. Just keep this in mind. A lot of these integrals are like this, where you'll have one trig term outside, one inside a complicated expression, and you're just going to do a u sub. Okay, let's evaluate. If you plug in pi, cosine of pi is -1, so you get 0. If you plug in 0, you'll get 2. So this is 32 over 20. 8/5. Okay, that's that example. Why would they do this twice? Yeah, I'm gonna skip this example because they're repeating it, but okay, this one's more challenging. Okay, so admittedly, some of these problems can be quite challenging in terms of what you're visualizing geometrically. So here's what they ask us. Find the volume of the solid. So find volume under a certain graph, 4 minus x squared minus y squared, and above the disk, x minus 1 squared plus y squared equals 1. We'll put x over here. So here's 4. 4 minus x squared minus y squared is 4 minus r squared. Looks like this. In the plane, it cuts out a circle of radius 2, right? 2 squared is 4, so that would be radius 2. We want to be, quote unquote, under this paraboloid. But we also have to be above a disk that's not centered at the origin. This disk is centered at 1, comma 0. So here's the point, 1, comma 0. And this circle has a radius of 1. So here is that circle. Whoops. Now, if you are above that circle, you lie within a certain cylinder. And that cylinder cuts the paraboloid somewhere. This is a challenging one. Something like this, maybe. Yeah, I mean, it looks like their picture in the book is wrong. 4 minus 2 squared is 0. Yes. Yeah, I don't know if anybody's following along in the book, but their picture is wrong. This book has a lot of these little errors. The way I've drawn this gold line, they kiss right there. That's mathematically accurate. In the book, they draw it like this, as if over this point there's a height. But that would imply that this function here is not 0 at this point, but it is 0 at that point. Okay, so unless I'm making a mistake, which I make tons of mistakes, it looks like that's a pretty egregious error in my opinion. But anyways, okay, what do we need to do here? We need a couple of things. Let's start with the domain. The domain is a disk, so we can call it D. Can we set up bounds over that disk D? Well, yeah, you can. So this is X and Y now. That domain is a circle, not centered at the origin. If we take theta to go from negative pi over 2 up to pi over 2, this is a polar region. Now, you might have memorized this. This is something people do learn. That can be given by, is it cosine of, 2 cosine of theta? We're going to prove this in a second, but you can get used to these curves that are not centered at the origin, but they kiss the origin. They are expressed by curves like that. But let's prove this. So you've got a x. So that blue circle there is x minus 1 squared plus y squared equals 1, which is x squared minus 2x plus 1 plus y squared equals 1. The ones cancel. You get x squared plus y squared equals 2x. Whoops, crap. God damn it. 1 second, guys. Sorry. Which is r squared equals 2r cosine theta. The square and the r cancel, and you get r equals 2 cosine theta. So that is a polar curve, this blue curve here. And therefore, we can integrate over it by taking the right bounds in theta. So let's go negative pi over 2 to pi over 2. We'll take r from 0 to 2 cosine theta. I've got dr on the inside, d theta on the outside. And I want to integrate what? I want the volume under this gold curve, or the magenta paraboloid. That's 4 minus x squared minus y squared, which is 4 minus r squared. That's the same as this 4 minus x squared minus y squared. And then I never, 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 never forget r. dr d theta, r dr d theta. If you want to integrate in polar coordinates, you must use r dr d theta. Okay, this one might be a little bit more annoying. Sooner or later, we're going to have to remember some trig identities, and I want to force that on you guys. So this is a 4r squared over 2 is 2r squared minus r cubed. Sorry, r to the 4th over 4. Did we get that right? 4r integrates to 2r squared. R cubed is r to the 4th over 4. From 0 to 2 cos theta d theta. Yeah, we're getting there. Here we go. 2 squared of 4 is 8. 8 cos squared theta minus 4 cos to the 4th theta. Yeah, because it's square 2, 4, 8, 16 divided by 4 is 4, d theta. And now there's a problem. It's not really a problem, but I must teach you the ideas. We don't have like a sine of theta to use for u substitution. You can't appeal to u substitution for these integrals. Take another moment, please, and remind yourself what are you supposed to do with these integrals. They call it a reduction of power formula, if I'm not mistaken. So cosine squared is 1 plus the cosine of 2 theta over 2. So those are the same. And now we got to do it twice. I really am just so against calculations that take so much work. Okay, so this is cosine of the fourth is cosine squared squared. Wait, let me sound it this way. Cosine squared squared. So inside I have 1 plus cosine of 2 theta over 2. That's the cosine squared, right? We just used that formula. But then I got to square it again because it's to the fourth. Okay, let's just keep going a little. We'll do these steps nice and slow so that everybody sees them. Negative pi over 2 to pi over 2. Okay, whatever. 4 plus 4 cosine 2 theta. If you square this 2, it cancels with that 4, and you just have 1 plus cosine of 2 theta squared. It's 1 plus 2 cosine 2 theta plus cosine squared 2 theta d theta. Woo! What a lot of work. Just make sure we got this all right. Um, yeah, so now what do I do? Right? Well, we're gonna do it again. Right? That cosine squared, we can reduce it again. So let's group everything. I've got 4 plus 1 is 5. 4 cosine 2 theta, 2 cosine 2 theta is 6 cosine 2 theta. Whoops, sorry. And then I've got to do it again. 1 plus the cosine of 4 theta over 2, all d theta. Maybe I'll do one more step and stop. I just want to make sure we're good. So if I group 5, so 11 halves. So okay, the 5 and the 1 half is 11 halves. Integrate that, you get 11 halves theta. 6 cosine 2 theta, that integrates to negative 3. I don't know, positive. So integral of cosine and sine plus 3 sine 2 theta. If you differentiate this, you get the 6 cosine. And then I've got plus cosine of the cosine 4 theta over 2, and that's going to integrate to over 8 sine 4 theta over 8 from negative pi over 2 to pi over 2. Right? The constant part, d theta, picks up a factor of theta, and then you got these two different cosine functions that each need to be integrated. Okay, whole lot of work. That's a good problem. I mean, it's a hard problem, right? There's like let me just kind of review it real quick. You've first got to geometrically interpret what it is they're asking you to do. Then, through the insights of that interpretation, you come up with suitable bounds in polar coordinates. Not only that, you convert your Euclidean expression into a polar expression. You never forget your Jacobian, sorry, this is called the Jacobian, we'll get there later, but your Jacobian factor of R. It's always R for polar coordinates. That right there, up until that point, the pictures and everything, that's what we're learning now. Then from there, it's really just a test that you've learned integral calculus, but you've got to integrate. There's some trig identities you should know. There's the techniques for reducing the powers of things, blah, 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 blah. And then if you don't make any mistakes, you're good. But really, up until this part here, so everything you see on the screen right now, that's really what you're learning right now. Below that is a review, um, but this is what's being learned right now. Let me see. There's not much time left, so let me pick the most important things to do. Give me 1 second. Uh, hold on 1 second. Sorry, guys. I want to make sure I didn't make any mistakes here. Yeah, they're with me up to here, and then they're with me on this part. Here we're disagreeing. So, 1 second. Oh, I see. Yeah, sorry. There is a mistake I made, right? This is 1 plus 2 cosine 2 theta plus these should all be minuses. Oof, terrible mistake. Minus, minus, minus. Boom, boom, boom. And now you get 4 minus 1 is 3. Um, so right here it would be 3. And 4 minus 2 is 2. And then this here would be a minus. And then one more step. 3 minus 1/2 is 5/2. And this is a 2 here. Is this another mistake I'm making somewhere? Sorry. Where's my other mistake? 4 cosine minus 2 cosine is 2 cosine. 4 cosine 2 theta minus 2 cosine theta is 2 cosine 2 theta. You gotta integrate, you get rid of that 2 there. Okay, so somehow they've got a 5/2 here. They might be mistaken about that. I'm not sure. Um, uh, so don't quote me on it. But let me continue because I can't tell just from looking right now. Okay, onward. There's one more problem that I wanted to do. Yeah, this guy right here. Okay, example. Find the area between the curves. Find the area between the curves. R equals 3 cosine theta. And R equals 1 plus cosine theta. We sort of just saw, and it's a review anyways, that 3 cosine theta is a circle like this, having a maximum radius of 3 right there. And then r equals 1 plus cosine theta. We just saw that too. That's a cardioid. And it goes as high as 2. So maybe 2 is right here. And there's a cardioid like this. Okay, but this part's not so important. The area between the two is right here. I'm going to try to make this very clear. We're going to do this as a polar integral in pieces because of these corners here. So first, we can integrate over this region here. We're going to need to know what the right choices of angle are. And that's not going to be everything because there's still these chunks here and here. Boom, 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 boom. There and whoops. And there. And for those two regions, we're going to go from theta 2 to pi over 2. Or down here, we can do from theta 1 to negative pi over 2. But there's a symmetry here. So we only need to find one of those. And similarly, if you want to, you only have to integrate from here to here. And you can also multiply and double that there. So let's do it that way. That's kind of nice. So first things first, let's just try to find this theta 2 angle. Well, if that angle occurs at the theta value where these two functions are equal, so 3 cosine theta equals 1 plus cosine theta. That's the same as cosine theta equals 1/2. Or theta, that positive theta right there, is pi over 3. Okay, so the purple region, first I'm going to integrate from 0 to pi over 3. R is going to go from 0 to the cardioid. The cardioid is the upper bound for the purple region. So this is 1 plus the cosine of theta. And I want to double this because I want the area down here as well. To find the area, I'm just going to integrate the function 1. If you integrate 1, you have a volume of height 1. That's the same thing as just the area. You never forget the r. This is dr d theta. And then I also need to do the region in blue. Again, we're going to double it because we're only going to do one of them. And I'm going to go from pi over 3 to pi over 2. And now I'm going to integrate not to the cardioid, but to the circle. Now the upper bound is the circle, which was 3 cosine theta. Again, I want to integrate the function 1. I never forget r, dr d theta. And okay, let's just get through as much of this as we can. Put the 2 with the r. That integrates to r squared. That's the first integral in r. Again, put the 2 with the r. Let's continue. Oh, it's a lot of stuff. 1 plus the cosine of theta squared plus 9 cosine squared. Okay, 1 plus 2 cosine theta plus cosine squared. That's 1 plus the cosine of 2 theta over 2. I can integrate this now. 1 cosine theta, cosine 2 theta, all integrable. Over here, same deal. And now everything that we can do. So integrating this first part, I got theta plus 2 sine theta plus the 1/2. That gives me 3/2 theta. And then I've got plus cosine of 2 theta over 2. So that's sine 2 theta over 4. This is from 0 to pi over 3. And then this next one, I got 9/2 theta. And then I need to also do 9/4 sine 2 theta. And this is from pi over 3 to pi over 2. And I'll stop here. I don't want to evaluate all this right now. But all the integration is done. You just have to plug in these guys everywhere, and it'll come out nicely. Okay, let me just do one real quick look at what everything we just did. Yeah, okay. So that is sufficient for 5.3. So I'll stop the video here. As always, please let me know if you have any questions. And thanks, guys.